Good morning, Algebra 2. Thanks so much for your participation today. I know I'm not here today, but this video will serve as what we were supposed to do today for Thursday the 19th, and this rounds up section 3.7, so we will be reviewing on Monday, taking our quiz on Tuesday. Don't forget that tomorrow is our first asynchronous Friday. If you have not already signed up for extra help and you want extra help, please sign up on the Asynchronous Friday sign-up sheet, which is in Schoology in the Asynchronous Friday blue folder that you can see there on our home screen. WebAssign is going to be due on Monday. WebAssign is open and ready for you to start. If you have not already started it, please make sure you're using Friday to complete that. Our asynchronous Fridays are going to be mainly focusing on WebAssign. If you have any questions or would like to work on those questions together, you know that you can sign up for the office hour time slots, so please do that. And if you have any questions or if you're confused with what's going on to round out this week, just please email me. So if you remember from yesterday, during class, we learned the beginning part of 3.7. So we looked at the graphs of functions, basic functions, f of x equals c or y equals c, f of x equals x, and so on. So we looked at all of these different graphs. We looked at graphs that are not functions, like this example here. This is not a function because this does not pass the vertical line test. The vertical line test says that if there's ever a spot in the graph where you would make a vertical line and it crosses through more than one point, that's considered not a function. So this graph crosses many different points on the same vertical line, which makes it not a function. We then looked at these graphs here to determine which ones were functions, and only the second and fourth one are functions. The first and third are not, because if you made a vertical line at several different points here, you would see that it would cross through more than one point, which makes it not a function. Today we're going to be looking at transformations of graphs and functions. So we can take graphs, parent functions we like to call them, and we can move them around vertically or horizontally. And here's what happens when you shift them upward, downward, to the right, or to the left. So if the function is its original function, like y equals f of x, to change it and move it upward, you add a number to the end of it, like here, so plus c. Anytime you have a number on the end, it moves it up. Anytime you do the opposite, you subtract a number on the end, it moves it down. So what's nice about vertical shifts, if you're moving up, you'll see plus a number. If you move down, you'll see minus a number. For example, if the equation is f of x, which again is a fancy way for saying y equals, if the equation is f of x equals, let's say, x squared, so it's a parabola. This is the parent function. If I want to move this function up 3 units, it would become plus 3 like that. That would move it up 3 units. If I want to move it down 3 units, it would be minus 3 like that. So moving up or down, it's nice because it's the same logic you would think would happen if you were moving it up or down. But moving it horizontally to the left or to the right, it's going to actually be the opposite. So instead of having a number on the outside, you actually have to have a number on the inside with the x. So if we're moving it left or right, you would have to have it say like x plus 3 or x minus 3. Now what's interesting about moving it left or right is when you have x plus 3 squared, it's going to actually move it to the left 3 units. And if you had something like f of x equals x minus 3 squared, this actually moves it to the right 3 units. And it's opposite thinking than you would think, like the vertical ones are exactly what you think. So if you look at like number 3 and 4 here, it says a horizontal shift to the right, you actually subtract. And a horizontal shift to the left, you actually add, which is opposite thinking from what you would think would happen. So if we look at these examples here, we are also using the parent function f of x equals x squared to sketch the graphs of these functions. So we want to sketch the graph x squared minus 2. So we can see here that the original function f of x equals x squared is this blue line here. And then because it said minus 2, that means it's going to be shifting the graph 2 points downward. So So it goes down 2 units, and then the graph, I'll highlight in green here, now looks like this. It's just sliding down 2 units. So whenever you have a number being added or subtracted on the end, that will be moving it up or down. And it's exactly what you would think would happen. If it's a plus, it'll move up. If it's a minus, it'll move down. But what's weird about moving left or right is when you have an original function, again, we're going to be using the same one, f of x equals x squared. That's this one in blue. That's this one right here. When you are shifting it left or right, it actually does the opposite of what you would think. This graph in green is moving to the left 3 units. So you're taking the blue graph and you're moving it to the left 3 units, but the equation is actually going to be this right here. They've got the little squared there. But when you're moving it to the left 3 units, you actually have to take the equation and put a plus 3 inside in order for you to get that new equation. And that's because the opposite of what happens on the inside is what will happen in reality, which is a little bit confusing. Now, you can always double check this stuff with your calculators. So if you get your graphing calculator out and I give you a question and I say, what's the equation of y equals x squared when you move it to the right 2 units? You could always practice this by taking your equation y equals, and to the right 2 units, you might do x plus 2 squared, and when you go to graph it, you would see that that actually moves it to the left 2 units. So you could use your graphing calculator to help you and be like, oh, okay, it must not be plus 2, it's minus 2. And then you hit graph and you can see it move in that direction that you want. If I said, what's the graph or the equation of a graph that's shifted to the right 2 units and up 3 units? You could then practice and think to yourself, okay, up 3 units also would be plus 3 at the end. Graph it and you can see it's moved over to the right and up 3 units. So you can use your graphing calculator to help you figure out the shifting and the way it works if you forget what the actual formulas are. On the next page of our notes here, we have another example of another function. Now this function is f of x equals x to the 3rd power. We're now moving this up 2 units. So we can see here the original is this one right here, and a cubic function looks like this. It kind of looks like a, I don't know, almost like an S. It's like this weird curve. And then when you move it up 2 units, you can see it drawn up here. You can use your calculator as well to see. Oops, not this one. You can use your calculator as well to see what happens if you wanted to put both of them in here. X to the 3rd power is the parent function. And then this one moves it up 2 units. So x to the 3rd power and then plus 2. When you graph it, there's the first one, there's the second one. So you can see what happens here as well. Things look a little bit different when you try to move it to the left or to the right. So in the next example here, we have the original function in the light gray, and then in the black, we have x minus 1 to the 3rd power plus 2. So it's shifted 2 ways. This one is shifted to the right 1 unit, and I can see that because of the minus 1 on the inside, and shifted up 2 units. So I can use my calculator again to show that I'm changing this by moving it to the right 1 unit, which would be x minus 1, believe it or not, to the 3rd power, and then up 2 units plus 2. Hit graph. You can see the original, and then you can see the new. Okay. And then we also have, in addition to shifting left, right, up, and down, we also have reflections. Reflections means actually taking a graph and flipping it over the x or y axis. So when you go to reflect over the x-axis, that means take the equation and flip it over the x-axis, and all you do is you take the equation and you turn it to its opposite. So you do the negative of it. For example, if we had the equation, let's say y equals, or f of x equals x squared. I know that this equation usually looks like this, all right? But if I want to flip that over the x-axis, and the x-axis, don't forget, is right here. If I want to flip it over the x-axis, it then will just flip it upside down like this. And when I do that, all you have to do is take the original equation, x squared, and put a negative in front of it, and it flips it over the x-axis for you. So if you look at these examples here, it says use the graph of f of x equals the square root of x to sketch these graphs. So the original graph of f of x, square root of x, is in light gray here. And then when you put a negative sign in front of it, it flips it over the x-axis. So if I use my graphing calculator to help show you what that looks like on here as well, if I put here y equals, which is the same thing as f of x, and I want the square root of x, you would have to hit the second button and then x squared. And then you would put an x here. If I hit graph, I can see what the square root of x function looks like. A little bit weird. It starts at 0. There are no negatives here, that's because they don't exist. And I can see the domain starts at 0, goes on forever, and it will just keep going like that. If I want to flip this over the x-axis, then all I need to do is put a negative symbol in front of the square root of x function, hit graph, and then in red I can see that this function is also graphed here. It's just flipped over the x-axis. Okay, and if we want to flip over the y-axis, you put a negative sign inside of the actual function. So if I just change this a little bit and I flip it over the y-axis, instead of putting the negative sign on the outside here, if I hit the delete button, and I want to insert a negative inside here, I hit second delete, and it'll allow me to insert in front. If I now graph that, I can see that the red line is flipped over the y-axis. Okay, so if we then look at this next page is asking us to practice, and these problems are hard. I'm going to model a few of these, and I'm going to ask you to please pause the video, try some on your own, and then press play so you can see me go over them. It will not be helpful if you just keep going through and writing it down without trying these on your own, so I really want you to press pause when I ask you to press pause and press play when I ask you to press play. So for these different questions here, I have 4 different graphs here, and this chart is asking us to identify the parent function and then if these different things are happening. So looking at this graph, I would have to use my notes from previous pages to figure out what graph this is. So if I scroll back up to this page, here are the basic functions, and the first one looks like this one. So this must be the parent function here, which is f of x equals x squared. I want you to get used to using that notation, so I'm going to use the f of x notation, but when you put it in your calculator, you have to use the y equals notation. So the parent function for that first one here, I know it doesn't look identical to it. That's because there's some translations that happened. This parent function is f of x equals x squared because it kind of looks similar to that first one in that it's like a U-shaped graph, but it's just upside down in this case. Transformation, so horizontally, did it move left, right, or none? It did not. It stayed right there in the center. It's not moved left or right, so I'm going to put none here. It did actually move vertically, though. So if I look at this, I know that the original parent function starts at 0, 0. It looks like this is moved up 1 unit. Is it reflected over the x or y axis? Yes, it is. I know the parent function of f of x equals x squared looks like a u. This one's flipped upside down, so it's reflected over the x-axis. The domain. The domain is all of the x values that will work for this graph, and any number from negative infinity to positive infinity will be the domain. I think the quickest way to write the domain is like in an inequality form. Negative infinity is the smallest x number. I know it's not a real number, but that's the smallest number it can be. And positive infinity is the largest number it can be. So the inequality would be from negative infinity to positive infinity. We always use these symbols for infinity symbols because you can never have an equal to part of it, since infinity and negative infinity are not real numbers, they're just concepts. The range of this actually is not going to go on forever, because if you look at this graph goes down in this direction, so it keeps going on forever for y values to negative infinity, but it stops. The highest point that this can reach is a positive 1, since the highest range number here on the y-axis is 1, so the highest number would be 1 here. You would use a less than or equal to number here, because it can be equal to 1. It's not an infinity. Like for infinity or negative infinity, those are just concepts, not numbers, so you can't use less than or equal to symbols for those. This is a function. It passes the vertical line test. And the function relation of this one, since it's flipped and it's moved up, would be negative x squared and then plus 1. You can always use your graphing calculator to help you if you don't have one. This is where you would want to use maybe Desmos online. I have those resources available on Schoology for you to go to, but you just Google Desmos calculator and you could use that. It's not as user-friendly as a TI-84, but it'll help. So that's the first one. I'm going to do the second one with you, and then I want you to try the third and fourth. So the second one, looking back at all of the different functions that I have, I know that the parent function for this one is f of x equals the square root of x. This one is not moved left or right, so this would be none. This is moved up. It's moved up 1 unit again, just like the first one was. This one's not reflected over the x or y axis. The domain, so looking at the x values, I can see that the smallest x value is going to be 0, and it goes on forever. So the smallest value in the domain is going to be 0 for this one, but then it goes on to positive infinity forever. Looking at the range, now I'm looking at the y values. I see that the smallest y value is 1, and then this graph goes on forever, so it's going to keep going to positive infinity. I need to change the symbol, it should just be less than, because infinity is not a number, it's just a concept. This does pass the vertical line test. This is a function, and the function's equation would be f of x equals the square root of x and then plus 1 since it's moved up 1 unit. What I want you to do, please, is pause the video and work on the second and third one. And while you pause, or when you're finished, I should say, please unpause, hit play, and then I'm just going to quickly go over those answers. So please pause, work on this one, and press play when you are done. All right, so the parent function for this, again, is f of x equals x squared. This is moved up. This is kind of weird, the numbering. It looks like this would be 3, I think. So it's moved vertically, not horizontally, so no horizontal movement, but it is moved up 3 units. It's not reflected over the x or y axis. The domain is going to be negative infinity to positive infinity because those numbers go on forever. The range, the smallest number on the range is going to be 3, and then that goes to positive infinity. This is also a function. And the function's equation, which you can use your graphing calculator to help you, is f of x equals x squared and then plus 3. The last one, the parent function is again f of x equals the square root of x. This one is not moved horizontally. This one is not moved up vertically or moved down vertically. This is reflected over the x-axis. So I know that I'm going to need a negative sign to show that. The domain of this still starts at 0, and any number in the positive x values will work. I can see here that the biggest number for this in the range is also 0, but then they're all negative numbers for y. So this is going to be the smallest is negative infinity, and the largest number that it is 0. This is a function, and the function's equation is f of x equals negative the square root of x. Okay, moving down to the next section, we have some more practice problems here. These practice problems are definitely still just as difficult as the first 4, but they are now requiring different types of functions. So what I'm going to have you do is try all 4 of these, but I'm just going to set you up with the parent function so I know that you're good to go, and then you're going to answer all of these questions. So the parent function for the first one, if you're looking at the beginning of 3.7, we can see that this parent function would be f of x equals the absolute value of x. When we have V-shaped graphs like that, these are absolute value graphs. This Parent function should look similar since we just spent a ton of time doing linear functions in chapter 3. This parent function is just x, like y equals x. Like using slope-intercept form, y equals mx plus b. The parent function for straight lines is just y equals x, or f of x equals x. This one is actually a horizontal line, and whenever we have horizontal lines, we just say that they're equal to c. They're just constant numbers. And then this last one, the parent function is a cubic function, which is x to the 3rd power. So what I want you to do, please, is try and fill out the rest of this stuff here. Look at the graph and see if it's moved up or down, left or right, reflect it, list the domain, list the range, and create your equations for all 4 of these. Instead of me going through in video form, what I have after this video is an answer key to the whole entire page, the beginning and the end, that I would like you to please fill in after you try it on your own. Like I said, it's going to go right in one ear, out the other, and not commit to your memory for your quiz on Tuesday if you just copy this down and not actually try it on your own. So I'm really asking you to try these problems on your own and then check the answers with the answer key, and that should bring you to the end of class. If you do have extra time and it's more time than like just a few minutes, please use the rest of the time to work on WebAssign if you want to use that time wisely and get some WebAssign problems done. If not, please work on WebAssign tomorrow during our asynchronous day. Don't forget to sign up on the asynchronous sign-up sheet that I have in Schoology and that I sent you in an email if you would like to work on WebAssign together. And I appreciate everyone's participation in today's lesson. Have a great weekend if I don't talk to you. But if I do, then maybe I'll see you on Friday if you sign up for extra help. And if not, then I will see you on Monday. Have a great weekend.